And that laptop is not plugged. Yes. Unfortunately, I will start about yes, I will start. That's what the only reason.
Okay, yeah. So, good afternoon, everyone. Um, this is our webinar, and then here we have Susan Toza from the scientific officer at SIMPA, at Center International Bureau of Mathematics, Pure et Appliqué, in Nice, France, since 2024. She also serves as a lecturer at Tech Nice Sophia, bioengineering specialty. After receiving a PhD on control models in fisheries in 1997, her postdoctoral research included positions at Ifremer, Nantes, France, 1997, Helsinki, University of Technology, Finland, 1997, and Institut de Cicero CSIC, Barcelona, Spain, 1998-1999, Marie Sklodowska Marie Curie Grant. She later directed her research towards crop protection. Susan's primary research application are in crop protection, pest and disease epidemiology, resistance management, sustainable control strategy optimization, with past work in livestock epidemiology, immunology, and fishery management. So I hereby introduce Susan Toza for her presentation on mathematical modeling and control for sustainable crop protection. Thank you. You're welcome.
Thank you. Can you see my screen?
Yes, very well.
Okay, sorry. Okay, so if I put it full screen, is it okay? Yes? Yes, is it okay? Can you see it now?
Yes.
Okay. Okay, so thank you very much for the invitation and thank you for the presentations. So I'm going to talk to you about mathematical modeling and control for sustainable crop protection. As I am a researcher in France, near Nice, where the SIMPA also is headed, and I'm a researcher at INRA, which is the French National Research Institute for Agriculture, Food and Environment, and I'm also part of an INRIA team, and this is another French research institute, this time for applied mathematics and computer science. So my research deals with crop protection, and this this research is in a global context of an increase in population and hence food demand, and a threat to this food security caused by crop pests and diseases. And we can see that a huge proportion of crop yields are destroyed every year. Moreover, agriculture is a major sector for employment and revenues in many countries, especially developing countries, and therefore controlling crop pests is a major issue. On the other side, that's on one side. On the other side, traditionally or classically, controlling crop pests relies on chemical pesticides, which have or can have a very negative impact on human health, on the environment, more, and with variable effectiveness, which really depends on the pest and the product. But globally, they can induce pest resistance. That is, that pests do not respond to these pesticides anymore. Moreover, they have fairly high costs in terms of money, of course, but also in terms of labor. So for all these reasons, what we really need at the moment are sustainable control methods that are alternative to chemical pesticides. Among these protection methods for crops, you can have different types of methods. You can have physical methods such as traps. The second picture on the right you see there to capture the pests, or you can have soil solarization, which is the first picture, where if you want to destroy pests in the soil, you put a plastic sheet and a bit of water, and so with the heat it can destroy some pests in the soil. You can also apply several cultural practices depending on the pathosystem, like rotation or strip cropping, which means cropping all the fruits on the trees after the harvest, or destruction of residues if the pest can be found in the residues, or fallow, or stump pruning, etc. Lots of cultural practices. You can also release biocultural agents, which can be microorganisms such as bacteria, fungi, viruses, or you can also use bio-derived chemicals such as pheromones to attract pests in other parts outside your field, or macroorganisms such as predators or parasites. You can also use the sterile insect technique, which consists in releasing the pest you want to find, but you release sterilized males. So when you release this male, they will mate with the females but have no offspring. So gradually you can hope to have the population decline because you overflow the field with these sterile males. There's also plant resistance deployment. So you can use plants, crops that are resistant, either completely resistant, that's qualitative resistance, but there may be a problem because this can be also broken. And then just as you have a resistance to pesticides, you can have pathogens that become virulent and are not blocked by a resistant plant. You can have quantitative resistance, which is polygenic. It's not complete resistance, but it is more difficult to be broken. And you can have tolerant plants, which are plants that harbor the pest, but still give satisfactory leaves. So all these are alternatives to chemical pesticides. I'll do a short introduction to epidemiological modeling. I don't know if all of you know about it, so it's going to be a bit fast. I hope it's okay. So this is in this context, what we use are models, and these models are these so-called SRM models, which represent the dynamics of an infectious disease in a population, which is broken into four, in this case, four groups: the susceptible, without healthy and naive individuals; exposed, which are infected, latent, or a non-infectious individual. Then you have the infectious individuals and the recovered individuals which can be immune or resistant, removed, etc. So this is the basis of this model. So first you have the first part is the force of infection, which transforms as susceptible individuals are in contact with infectious individuals, they become exposed individuals. Then after a certain latency period, they become infectious individuals. The duration of infectiousness being 1 over gamma, they then become recovered individuals. And in this model, we assume that immunity is not for life, and then after some period, they become susceptible individuals again. So this is a basic model. we see that if we add the 4 differential equations, it adds to 0. So we know that we have a constant population that we will denote by P, which is positive. And there are 2 equilibria. One that always exists is the disease-free equilibrium, where all individuals are susceptible and there are no infectious individual in the population. And then there's the endemic equilibrium, only if the parameters verify the inequality at the bottom of the slide. And this means that this is an equilibrium with the disease. Then there's a threshold that's really well known in epidemiology. It's the basic reproduction number R0, which basically corresponds to the number of secondary cases generated by an average primary case or index case during its entire infectious period when it is introduced in a fully susceptible population. And this threshold corresponds to the local stability of the disease-free equilibrium. If it's less than 1, there is no epidemic. The infections cannot settle in, which is the case in the picture you see here. We have an R0 of 0.5, and you see that in green you have the susceptible individuals. At the beginning, all individuals are susceptible except 1 infectious individual, and well, fairly rapidly, then you have all individuals that are susceptible. So this is the case when R0 is less than 1. If we increase R0 even at 0.9, you see that the same happens, although it is a bit longer. It takes a bit longer, and then you see a few recovered individuals appearing, but then everybody becomes susceptible. So in this case, we say we have this stable disease-free equilibrium. Then we have R0 equals 1, and then we have R0 equals 1.1. And in this case, as it is bigger than 1, we have an epidemic, although a small one in this case. And then we have the DFE and becomes unstable. And you see that at the end, a few individuals remain infectious or recovered. And if we increase, it becomes more and more. So you see that after some time, you always have in the population susceptible, but also infectious individuals. And even more if you increase or not. So this is the basis of epidemiology, which is usually more applied to human population or animal population, but less frequently to plant populations. And this is what I'm dealing with. And you have a few specificities when you deal with plants compared to animals or humans. At first, the definition of an individual is fairly complicated compared to plants and to humans and animals. Do you consider that an individual is a plant or a tree, or parts of a plant or a tree, like a leaf, or is it a root or a fruit, etc.? So the definition of individual, because the populations we consider are populations of individuals, is not that obvious. You can have on a plant leaves that have the disease, but the entire plant is not unhealthy. Plants are also affected by diseases, but also by pests like grazers or phytophagous insects. So it's a bit different. And especially plants don't move. So the contacts you are seeing for the infection are not direct contacts. They happen via vectors, via the wind, water, or free-living pathogen stages. Another specificity is that plants usually don't recover. The R stage we saw for the human and animal populations is not very usual. However, they have variable susceptibility. And this is all for plants. And when now we talk about crops, so these are plants that are managed by humans. So you have to take into account planting, harvest, partial environmental control if you're in a greenhouse, or even on a plot where you'll work on this plot. in all these cases, there's a huge role played by seasonality. In annual crops, of course, because then you have the season that comes for the annual crop, but also perennial crops, because you have harvests that occur periodically. So these are the plant and crop specificity that we're dealing with when we are looking at plant epidemiology. So the approach we have in this case is to design and analyze epidemiological models, that's the ones you saw, but adapted to plants. And we do that for several reasons, because we want to better understand the plant-parasite interactions, how they work, and we can also test hypotheses, sometimes because we want to predict the evolution of damages, or also because we want to design efficient and sustainable control strategies, in the sense that we want to limit damages and crop losses. So I will focus more on this third goal in the talk I'm giving today. And to do so, what our approach is to use tools from the optimizations and also from control theory. I told you that crop systems were a bit different from plants and from humans and animals, and so the pathosystems we're going to consider here can have either with single cropping season or multiple cropping season, and can be seen at different scales. So when you deal with crops, you can consider the single plants up to the landscape. In this case, we'll focus more on single plant or globally on a field, although we do work at these different scales. So this is a brief introduction to what I wanted to present you, and what I'm going to do now is to focus on an example of research we have been doing, and it's on optimal control for banana-bearing nematodes. It's part of Franck Emayo's PhD thesis. So Franck is a student at the University of Douala, which we co-supervise with Frédéric Grognard and Samuel Boron. And during his PhD, he had the opportunity to come to France, thanks to INRIA and Ambassade de France funding a few times. And the work I'm going to present here is was also done in collaboration with Walid Jema, who is a colleague from INRIA. So I will say a few words about the pathosystem. So bananas, you may know, including plantain, are major staple food in Cameroon, where Franck comes from. It's more or less 2% of the GDP. It's a plant that whose cycle is more or less 11 months. And one of the major pests for these plants are boring nematodes. So nematodes are small worms in the soil that develop, feed, and reproduce in the roots of the bananas. They are less than 1 millimeter long. They have to go inside the roots to complete their cycle, and they can reproduce through sexual reproduction or hermaphroditism. So males are not infected, it's only females. The life cycle of boring nematodes is 20 to 25 days, so it's much shorter than the cycle of a banana plant. What they do when they infect the banana roots is the picture you see on the right. When it's really severe, it's they reduce the nutrient and water uptake in the plant. So this is going to reduce the production of bananas, and it can also weaken the anchor roots and can lead up to plant toppling. So you see there a plant that is on the ground. So this is the most serious damages. So because of this, there are there have been some research in the control methods. So the first ones, as I was telling you, classicals are chemical nematicides, but they're very, very harmful to the environment and for human health. And in most European countries, at least, they are completely banned. This substance cannot be used anymore. You can try to do soil sanitations and use vitra plants from nurseries that are nematode-free plants, or you can use tolerant or resistant banana cultivars, although they're not that frequent, or you can use biological controls. For instance, you can use biostimulants that enhance plants' defense. What we're going to do in this talk is focus on biological control, as biostimulants, as we had beforehand tried to look at soil sanitation in vitra plants in the case of Israel Tankam-Shetsh's PhD, which was defended some years ago. And the question we want to address here is how to control banana-boring nematodes to optimize profits. Is everything okay? I hear some noise. No? Okay. So I'll just continue. So I'm going to build the model.
Thank you very much.
Go ahead, please. Okay, thank you. So I'm going to build this model for a single season. So I'm going to consider my population. So divided into roots and nematodes, and within each of these populations, I have subpopulations. So in the roots, I have the susceptible roots and the infested roots. And for the nematodes, I have the free-living nematodes that are in the soil but are not in the roots, and the infesting nematodes inside the roots. So the first process we have in this model is the infestation. So there we have free living nematodes in the soil that are going to infest susceptible roots. And so susceptible roots become infested roots, and free living nematodes become infesting nematodes. So this is the first process. We also include in this model, or maybe it's another type of infestation. It's nematodes that are already in the roots, but are going to migrate within the roots and infest roots that were previously susceptible, but that will also become infested. So we have these nematodes that are within the roots that can also infest susceptible roots when they migrate into the roots. As a consequence, the nematode density within the roots is not constant. It is variable. Then we have another type of infestation. The nematodes within the soil, so the free-living nematodes, can also sometimes choose to not infest susceptible roots, but roots that are already infested. And in this case, that will also change the infestation density. So we have three types of infestation. It's free-living nematodes that can infest either susceptible or infected roots. And then we also have the infesting nematodes that are migrating into the roots and are then infesting new and susceptible roots. So these are the epidemiological, let's say, processes. Then we have sometimes migration for sometimes when the density of nematodes within the roots is too big. Then we have migration from nematodes that are within the roots that go back into the soil, so become free-living nematodes. So this is migration. Then we have root recruitment. So we suppose that root recruitment is constant per unit of time. So the roots are growing and they're susceptible. And we also suppose that the nematodes within the roots are growing. So they're growing with a logistic-like function that is depends on the density of nematodes within the roots, infested roots, and this is what limits the nematode growth. So Ni divided by I is the density, and it cannot be higher than the kappa. So we have a maximum density within the roots. But this growth is also, you have the basic growth with the basic growth rate R, but you also have the growth rate that depends on the root consumption, because they feed on the roots. So if they can feed on the root, then the growth is even bigger. So we have this root consumption term, which creates have roots to necrosis, so infected roots disappear, and then we have and then we have this nematode population that increases. And finally, we have motility term in all the compartments. Right. So this is the whole model with the 4 compartments. And we can show that this model is biologically and mathematically well posed. We have all the variables that are non-negative or even positive, and they are bounded. Please note that because we have a density Ni divided by I, so the density of nematodes in the roots, this model is not valid when there are no nematodes. So we suppose that the nematodes, the infesting nematodes and the infested roots are always positive. They cannot be 0. What we're going to suppose now is that infestation, so nematodes from the soil coming into the roots, is a very fast process compared to the other processes, which is fairly true. Nematodes do not remain in the soil for very long. They migrate during a short period of time and re-enter the roots. So when we do that and we use Tikhonov's theorem, we can reduce the system to the system you have now, which is much simpler and is a good approximation of the whole system. So from now on, we're going to work on this reduced model that has 3 equations. And as I was saying, is a good approximation. So the scheme of this reduced model is shown on the right. And so you have three variables now. You have the susceptible roots S, infected roots I, and the total nematode population N, which is supposed to be mostly or almost only within the roots. For this system to maintain itself, we need to have that the basic growth rate of nematodes R is greater than the mortality of the nematodes nu, which is fairly obvious. So we suppose that this is always true. Doing that, we can look at the equilibria of this system. So we have first a pest-free equilibrium, which is, as I was telling you, it cannot be defined in this system, but we change the system, we change the variables, we consider the S, I, and variables as the other, but we replace N by the nematode density within the root X. And then we can look at the pest-free equilibrium, and we can show that there's a threshold R, which is not exactly R0, but still a threshold. And if it is less than 1, then this pest-free equilibrium is stable. Now, if we want to look even in this reduced model with 3 equations at the endemic equilibria, so an equilibrium where we have susceptible infected roots and nematodes, there's no explicit expression because we have to solve a degree 4 polynomial. However, we can show that if R0 is less than 1, we can have 0, 2, or 4 equilibria, endemic equilibria. And if R0 is more than 1, greater than 1, we can have 1 or 3 equilibria, depending on the parameter values. So to look that a bit further, we did a bifurcation analysis. So we varied parameter beta, which is the infection rate. We kept reference parameters, and we And in some cases, we change two parameters to highlight two very contrasted cases. So if you look at this bifurcation analysis, we first see that with the reference parameters, when we vary R, and R is varying because we vary beta, the infection rates, we can see that we can have the bifurcation diagram on the left, where we represent the infected routes at equilibrium as a function of the R value. So we see that when R is greater than 1, we have a unique endemic equilibrium. And we show that it exists and that it is stable. We can see that if we choose R equals 8.4, which corresponds to our reference parameters, we obtain on the right the dynamics of the system of the infected routes. And we see that starting from two different initial conditions, we have the convergence towards the infected an infected root value that is greater than 0, a positive value. So this corresponds to an endemic equilibrium. In some cases, when we vary other parameters too, we can have a backward bifurcation. And in this case, even if R is less than 1, this does not ensure pest eradication. So if we look at the bifurcation diagram on the left, indeed, and we see that, for instance, so it's the same bifurcation diagram, we have the infected routes at equilibrium as a function of R. We see now when R is equal to 0.5, that's the dotted line, we have the pest-free equilibrium, which is stable. Then we have a non-stable disease endemic equilibrium, and then a third stable endemic equilibrium. So although R is less than 1, we can have an endemic stable equilibrium, meaning that pest eradication is almost impossible. And we see that on the right, when we see the dynamics of the system for the infected routes. So we see that in some cases where we will converge towards the pest-free equilibrium. So it's for R equal 1.5, but in some other cases, we're going to converge to an equilibrium with positive infected routes. So we have bistability in this case. Okay. So now I'm more interested into control. So as I was telling you, we are going to introduce biostimulants that are supposed to enhance plant defense, that is, reduce infestation. So if we look at the model, what happens is we add this term, the red term, on the infestation term, and we suppose that the control U is between 0 and U max, which is less than 1. And this, when U increases, this reduces the infestation. So it means that the plant defense is higher. So this is the control model. And what we're interested in is, so we are applying the optimal control theory. We're looking at a finite horizon. So we're going to consider a time interval 0TF. We're going to consider all the controls that can be defined on this interval. And our aim here is to find the control that is going to maximize the profits. So the profits being the yield minus the control costs during this cropping season, 0TF. So if we look at these two terms in J, the first one is the yield. Indeed, it's the integral of the susceptible roots during this cropping season, because it is a good proxy of banana production, the integral of susceptible roots, because it corresponds more or less to the nutrients that the plant can absorb to build the fruit. So the first part is the yield with, you can say, think that BS is like, is related to the price of the fruits when you sell them. And on the right, you have the costs. So U is a control, but when you apply it, it has a certain cost because you have to buy the biostimulant and you also have the labor costs. So these costs are integrated along time, and they are and the unit cost is given by BU. So this term corresponds to the profit. We also integrate a penalty in this criterion, because we also want to minimize the infestation at the end of the season. Why do we do that? Because if we don't, the best strategy will probably be to control at the beginning, but not to care about what happens next, what happens for the next season. And we are interested, although we are applying this control during a season, we're still interested in the next season. So at the end of the season, we want to have as little as possible in infected roots. So this is why we have this penalty in this criterion. So we want to find the control U that is going to maximize this function J of U. So this is the optimal control problem. And how does it work? So you can we can apply the Pontryagin's maximum principle, which is saying that the solution to this problem is a bang-bang solution. And to solve this problem numerically, we used a direct methods provided by the Bookup software you can find, which is a free software on GitHub or bookup.org. So the results we obtain are here. So here I represent the 3 state variables. So top is the healthy roots and infected roots. At the bottom, you have the total nematodes on the left, and on the right, you have the optimal control. So these are dynamics along time. In black is what happens without control. How does the system behave without control? And in red is how the system behaves with optimal control. And on the top left diagram figure, the healthy roots, you also see the level without pest. If there's no pest, you can have 6,000 healthy roots. That's the maximum you can have. So what we see is that this control, if we look at healthy roots, and that the optimal control manages to maintain very good level of healthy roots, especially compared with the case without control, the black one. There are twice as many healthy roots. If we look at infected roots, well, there are a few infected roots, but they're half compared to the case without control, or even less. And there are some nematodes, and they're oscillating. They remain fairly low, especially compared to the case without control. And we have all this oscillation because the optimal control we see is oscillating. It is like, it is bang bang, so 0, Umax, 0, Umax, 0, Umax, etc. And well, it is a bit, there is no seasonality in the system. It's just the control that is like this. So this was a bit surprising. However, it is very efficient, as you can see. So we changed a few things. So remember the penalty at the end. I said we wanted also to minimize the number of infected roots at the end of the period. So if we do not apply this penalty, what happens? Well, when we get to the end of the time horizon, then, okay, there's no control anymore. You have a bang 0, so you don't control anymore, apply no control. So the nematodes increase, they infect a lot of roots. So the infected roots at the end of the period are very high, and the susceptible roots decline. So this is what happens if you don't put the penalty. Now we're looking at what happens if we change Umax. So I was telling you, you can vary between 0 and Umax, which is less than 1. And then we reduce this Umax. And what happens is that the best strategy is to control almost all the time. And why is that so? And because it's cheaper. So you control almost all the time, as you see, but still you don't get a very, very good result because it's not efficient enough. So what happens in this case is that the control is not efficient enough. It's cheaper, but not very efficient, and so the oscillations disappear. So this is the result of the optimal control. Because of this oscillating control, we wanted to have a look at other types of control and compare it with what we call suboptimal control. So the first idea was to look at constant controls. How does this compare with constant controls? So the first or most obvious constant controls is to check what happens if we just take the average of the optimal control and apply it all the time. The yellow line here is the average of the optimal control. So on the top figure, you have the control, and on the bottom, you have healthy roots. So black is no control, red is optimal control, dotted gray line is what happens if there's no best, and so this yellow line is average optimal control. Well, this is really a very, very bad strategy. If we look at our criterion J, it is much, much better with the optimal control. So, okay, that was the first idea of a constant control. Another one is the so-called static optimization. So it's just to look at the endemic equilibrium and try to optimize the control at this endemic equilibrium. So this corresponds to the blue line in this case. So it is the control is much, much higher than the average, as you see. It's much higher on the upper curve, upper figure. And you see that you obtain the healthy roots you obtain are very good, but it is not a very good strategy because the control is very expensive because you apply a very high control throughout the whole period. So it's going to be very expensive, and this is going to penalize the criterion. So the criterion is not very good. It is better than the average control case, but not that good. Then we said, okay, let's optimize the constant control. So we look at the best possible of a constant control. So we solve the optimization problem and we obtain the purple curve, which is very close, almost similar to the static optimization, which is kind of expected and would be even more if the time horizon was longer, because this would then you would have converged towards the equilibrium. So they would be very similar. So both are okay, but not that good. So constant controls, all the ones we could think of, are really not as good as this oscillating optimal control. So then we looked at periodic control. So we optimized a 3-parameter control, periodic control, where we set the first lag at the beginning. When are you going to start the control? And then we also optimized the upper band and lower band durations. So this is an optimization with 3 parameters. And what we obtain in this case, it's the green curve. It's almost similar to the optimal control. There's a little shift, and the criterion is completely similar. So, which is expected because as you could see the optimal controls was almost periodic. Right. So on this case, what's the take-home message? Well, we wanted to know how to control banana-bearing nematodes to optimize the profit. And the very counterintuitive result we got is that oscillating controls outperform constant controls. They're much cheaper in terms of control costs because you don't need to control all the time. They're almost as efficient to maintain a healthy root biomass and hence to maintain the yield. And for practical reasons, applying periodic pest control is fairly easy. We also saw that in these results that we need to have a biocontrol method that is efficient enough, because we need to reduce the pest infestation rates fairly it has to be fairly high. In our case, it was 80% reductions, which is fairly high. So if we want to have an efficient biocontrol, it would be certainly more realistic and more efficient to combine it with other pest control methods, such as soil sanitation. So this work, as I was saying, is part of Franck Emaille's PhD thesis, and this has been formalized in a paper, which is now you can find as a preprint on the HAL archive. This work was extended, and this is still ongoing. So we were looking at a single season previously, but then we wanted to look at this model over several seasons. So what you see here is the model during one cropping season. This cropping season starts at NT plus and ends at N+1T. So this is what happens during the cropping season. Then you have the uprooting. So when the plant has produced the bananas, then you uproot the plant, and then you uproot the old plant, and you keep one of the upshoots for the next season. So when we do that, what we say is that when we uproot the plant, we start with a new plant that has a constant root biomass gamma 0. So the new plant, after uprooting, has always the same biomass gamma 0. And we assume that when the mother plant and the young plant, the young upshoot that is kept for the next season, have the same prevalence. So the proportion of infected roots in the mother plant and in the upshoot are the same prevalence. So this is what happens during the uprooting. But what could happen is they don't have the same prevalence, but through some kind of control, that could be also looking at the plant, and if there's an upshoot that is better than the other ones, choosing this one or whatever, then maybe we can have a reduced prevalence in that case for the next plant, And then we assume that the density of nematodes in the roots is the same before and after uprooting. So these are a hypothesis for what happens when the plant is uprooted. So when the banana bunch is harvested, the plant is uprooted, and you keep one upshoot. With this hypothesis, we have the whole semi-discrete model as follows. So we alternate cropping season and which are dynamic, continuous time dynamics, with uprooting, which is a discrete event. And at all this discrete event, we have the equations on the right. And for the dynamics during the season, we have the same equations as beforehand. So this is the multi-seasonal model, which is a semi-discrete model. So we did some analysis of this model. We looked at what we could say about, then we don't really have equilibria, but we have what we call periodic solutions. And the first thing we could say is that the basic properties are okay. And then we looked at this periodic pest-free solution. So this corresponds to the pest-free equilibrium, but this time it's a pest-free solution. And we could, I didn't give all the computations here, but we can see that in certain cases, for certain parameters, we can say that the periodic pest-free solution is locally asymptotically stable, which is illustrated here. So you see that top left is not infected roots, but susceptible roots. And so you see that on the top right, the infected roots are going down to 0, that the nematodes on the bottom left are also going down to 0, and that the susceptible roots at the top top left are oscillating and are periodic. So this is a case where the periodic pest-free solution is stable. In other cases, well, it becomes unstable. So you see that the healthy roots are still periodic, but at a lower level, and we see infected roots that are also periodic and then don't converge towards zero. We also have nematodes that are periodic, and we have we can show, but only numerically, that we have a stable periodic endemic solution in these cases. What is ongoing now is well, to look at the control in this multi-seasonal model. So we could have a similar optimal control problem with the same control U to reduce infestation during the cropping season, and we could also look at maximizing the profit during end cropping season, and we can use the hybrid Potiagin's maximum principle and try to obtain bang or singular solution. This is still ongoing, but in this case, we can also apply other control strategies, because we saw that when we uproot the plants, we could reduce prevalence. Like, it is possible to reduce the prevalence at uprooting. So this would be another type of control, a discrete control. So we could look at this discrete control, or even better, combine both control. The control during the cropping season that reduces infestation, and the control at uprooting, which reduces the prevalence. So this is work in progress. So this is all I'm going to say now about this. And I'm looking at the time. Okay, I wanted to show you another example, but it's maybe a bit short in time. What do you think? It was just the modeling. Shall I just conclude and leave a bit of time for questions?
Are you still making, since you said you are leaving by 4:15?
Yeah, I have to leave at 15:15. Yes, I'm sorry. In a quarter of an hour. So what?
Maybe we go to questions.
Go to questions. Okay. So this was just. Yes, questions?
Yeah, question now.
Okay, I'll just conclude. So I had another example, but I'll just conclude now. About this modeling crop pests and diseases with strategies that are alternatives to pesticides. What we're doing with this modeling approaches is really getting insights in sustainable control deployment. It's not totally realistic, but still you can have some conclusions that are very interesting, such as this control should not be constant, but it's more efficient to have it oscillating, etc. Of course, there are simplifications, for instance, here, and there are still a few challenges that small data, because we have very little data in this for plant epidemiology, and maybe a link with remote sensing would be appropriate. And then it would be interesting to introduce growers' decision. In my second example, I had a bit of more of this, but this is going towards behavioral epidemiology. These are two things that I would be interested to see a bit further. And I just wanted to say that this work was done within the EPITAG framework, which is an associate team between France and Cameroon. And it's based on this co-supervision of PhD students. Until now, there have been 4 theses that have been defended and 3 that are ongoing. So thank you very much. And now we can have the questions.
Okay, thank you. Can we give a round of applause, please? Okay, so questions from the what's online the site. Question? No question. Okay. 1, 2, 3. Thank you. So, yeah.
Okay. Hello, can you hear me?
Yes, I can hear you.
Okay, thank you for your beautiful presentation. My first question is, and that will also lead me to other questions, particularly about the model you showed on slide 11. I want to ask, do free-living nematodes, are they parasitic?
Yes,
Uh,
yes,
free-living-
I'm sorry, I'm trying to find my, yeah, they are parasitic nematodes. I don't know what's happening with my,
slide 11.
slide 11, yeah, sorry. My, okay, I have it, slide 11. Oops, sorry. Yes,
All right, so you said they are parasitic, right?
yes.
So what's the difference between free-living nematodes and then the infected nematodes?
Okay. So although they're endoparasites, from time to time they leave the roots, okay, and they leave the roots and they migrate in the soil and find new roots. So usually they are very, very little mobile. They stay within the root system. So to contaminate another plant, roots have to be quite close, or they have to be brought by humans or by water. Water can do that. But they can be found in the soil, and especially sometimes the reproduction also occurs either in the root or just outside the root. So you can find a few nematodes in the soil, but it is true that most nematodes are within the roots, which is also why we did this simplification and this reduction.
All right, thank you. So lastly, I want to know, can you briefly explain the dashed arrow that moved from the S compartment to the NF line? The arrow that moved from S to NF. Can you explain that?
This arrow here, S to NF?
Yes.
Oh,
Yes.
it's just no. It's not. It's not. It's a dashed line, so it's not. It's not an inflow or whatever. It's just to say that when it's for the infestation. Okay, it's just to say that the infestation. So what makes free living nematode become infesting nematodes is also depends on S. So to become an infesting nematodes when you're free living, it depends on S. It's proportional to S. This is just to indicate that this flow is depends on S.
All right, thank
Okay, yeah, thank you so much. I have about 3 questions to ask. The first one, I saw that in the control that you put, for the control, are there possibilities of the control waning over time, or once it is used, it's there throughout the period?
The control waning over time. Okay, this is a continuous control. Okay, so this is a continuous variable that depends on the time. And the hypothesis we do, which is not necessarily realistic, is that, okay, the optimal control we obtain here is how should we apply the control? So this means that at first we should do nothing, then we should apply the control during this period of time, then do nothing, etc. So your biostimulants, when you apply it, we think we have no persistence. If you stop applying it, we don't assume that it's still in the plantation, which is also simplifying hypothesis, but we have been looking at some persistence. So when you apply it, it remains a bit in the there's a decay, but it remains in the plantation for some times, even if you don't apply it anymore. Yeah, a good question.
Okay.
Thank you.
Yeah, okay. So why I ask that is because, when I look at the bang control that you have here for the optimal control, I saw that over time, at a point you have 80% to be used for some time, and then after some time 0, and later 80% over time. So I'm looking at the time profile now, like what determines the time when it is applied at that
Which
80%, and then when it becomes zero, and then that's oscillation that we have in a bank control.
Yes, well, that's something we try to investigate. What the switching times, how they are determined. So when you apply Pontryagin's maximum principle, you have adjoint variables, and you can see you have the switching function, etc. But it's not very obvious. And we looked even numerically when it was happening, and in fact, it's very complicated. We don't know, because even when we change the initial conditions, the switching times are different. So which can be expected, but we don't really know what they correspond to. We tried to see if they corresponded to some values, or from the equations, they were a combination of variables that could explain when we switch, but it is absolutely not obvious. So we don't really know why we have this switch and when it occurs. We have to solve the optimal control problem to get this solution.
Okay, because I'm very much concerned about the implication of that for control nematodes in banana, particularly for people on the field who may want to be interested in. So when do we deploy the maximum control? When do we relax the efforts and all of that, which is something people on the field want to be
Yes.
interested in. So that's why I asked that question.
Yes, no,
Right.
this is true. But this is open loop control. So it means that you have this, you say, okay, this is the optimal solution, you apply it, and you don't look back to what happens to the other variables. And if you want to have a more robust control, closed loop control will be more appropriate. And we could also, what we haven't done, but we could also look at the robustness of this solution. If we change a bit, if we don't apply it exactly on time, but a bit shifted, what happens? And when we did the suboptimal controls, especially the periodic one here, we saw that periodic controls, even if they're not completely as close as this to optimal control, sometimes they were a bit shifted, etc. They were much, much better. So this at least says that you should, at first it's not necessary to apply the control, and then when you apply it, you have to do it, but not, you have to do it, put a lot of biostimulant, but not, because it's too expensive, not do it all the time. So do it fairly frequently. And this is fairly robust. It is suboptimal, but fairly robust.
Okay, thank you. So the last question I have now is now, because the question you posed earlier had to talk about reducing the cost in order to maximize profits. So I didn't see you talk about the aspects going forward during your presentation again, like in terms of the profits now. Profits.
Okay,
So I didn't
the profits are inside the J here. J corresponds to the criterion I am optimizing, and this corresponds to the profit, or the penalized profit, if I apply the penalty at the end of the season. So profits, J is the profit.
So you mean profit in terms of the yield, right?
In terms of, sorry, I didn't get it.
You mean profit in terms of the yield, you maximizing the yield. You mean profit in terms of maximizing the yield.
Profit, what I am profit here is yield minus costs. In terms of money, financial profit. I'm sorry, maybe I didn't get it properly.
What he's asking is that the profit is a function of what? Is it a function of the yield?
It's a function.
At the end of the function of the yield, the profit.
The profit
at the end of the day, it's a function of the yield, right?
It's a function of U and S. but they're all interdependent. If you apply a certain U, it will affect S, I, and N. So it's this function. The profit is this function.
Now, practically, when you make use of control, are you getting me?
It's not very good. Sorry, the sound.
My voice oscillating.
Yes, your voice is also oscillating. Sorry.
Okay, can you hear me now? Am I clear?
Yes, that's much better.
Like for, I mean, you have a single control, and then we are trying to find that the optimal control by maximizing the profits based on the yield minus the control cost. So
Exactly.
the question now, so the question now is now, what is the profit? Does the profit has to do with the yield?
No, the profit is really yield minus costs. It is what the money that you have in your pocket. So when you sell your production, it's the yield, but you have to buy the products and apply them. So that's the cost. And so profit is yield minus costs. And sometimes you have this penalized profit, this penalty on top. Is that clear?
Thank you. I also have some questions for you.
Yeah, so thank you for the beautiful presentation. So my question has to do with the reproduction number. So I want to
Threshold.
okay. Threshold, okay.
So, I mean, for this, it's not, I was saying it's not reproduction number because this is not, this has not to do with human population. This has to do with the plants and is a threshold condition you define, right?
Yes, that's it. It could be interpreted as a reproduction number. It's close to a reproduction number, but it's not exactly the reproduction number.
So my question one is that the model, I was thinking of the parameters. I didn't see the parameter table, and then
no, I didn't put it here. I thought it would not be very readable, and it would go very fast. Yes.
I was thinking that you were going to carry out some sensitivity analysis to know some of the parameters that are driving the transmission now in the plant and transmission dynamics of that pest. So I mean, because like going for optimal control, I mean, there should be a kind of sensitivity analysis for you to be able to, because I saw that you got a threshold, and then the question was that there were some parameters in the model that were not inside the threshold condition. So I was beginning to look at, okay, does this threshold condition really capture all the parameters in the model? And then also on the aspect of you put up the seasonality. I mean, the last one that has to do with seasonality, you know, like the seasonality was somehow compacted because the time unit you used was in years. So for you to really see the seasonality was, I mean, I'm beginning to look at that I think the seasonality should open up to weekly and monthly data, and then you'll be able to see more seasonality than the yearly. When your y-axis was, I mean, the x-axis was on years in terms of the unit. If you look at slide 25, is it 25 now? Yes, this one. So the unit of the time here, I mean, is going to limit us not seeing certain things, you know. So in terms of the seasonality, because seasonality has to do with what's it called? Systematic or periodic infection at certain times of the year. So I mean, either it would be good that you look at it in terms of weekly or monthly, and then we'll be able to see the peak of those infections at certain times of the year, not just yearly. Within the year, let's assume that within a year. So, and then if you put it in months, we'll be able to see more, or week.
But
can
it is,
see more.
although you have these discrete jumps each year, because it's an 11 month, and it's not exactly a year, because I was telling you the cycle is 11 months for the banana tree, or banana plant rather. But then you have, in between, you have a continuous dynamics. So you have day or week or whatever. It is continuous. It is continuous dynamics with jumps that occur each 11 months or almost each year. This is what I'm representing. So this is a semi-discrete model. It's continuous between two jumps. This is a continuous model.
Okay, but
as you can see, it may be better for the endemic. This is a continuous model. This is how the density or the roots are going.
I also love to see the unit of your parameters, to be able to see how they align with some of these, maybe another time, but I've been good that we see, because parameters tends to some certain level of uncertainty. So because if we see the parameters, it will also like help us to see how the model is behaving, because the parameter play a very strong role. If we know the units and then the bounds of the parameters, whether they are fixed or they are within certain variations. So because of uncertainties.
Yes, so the analytical results are, of course, independent from the parameter values. And so we can see that we can, of course, look at the variations of this threshold for the single season, these thresholds in terms of robustness to parameter uncertainty. And this R is deciding whether the disease-free equilibrium is stable or unstable, or the endemic is there. So we can use this. And for the regarding the multi-seasonal model, we also have some analytical results for the stability. So we do have a few results on the local stability of the disease-free equilibrium. So if we find a control that can bring the system below this threshold, then we know that we can control the pest. So we do have that in terms of analytical solutions. When you do optimal control, of course, it's parameter. The solution is numerical solution depends on the parameters, and we could also do some kind of robustness analysis. So yes, there's more to do. We can also look at do sensitivity analysis, but we'll have to see on what. What we're looking at is efficiency of the control. So as I was telling you, when we look at periodic control, we saw that even if it's suboptimal, it's still fairly good. I'm sorry, maybe a very last question, because I'll have to go.
So maybe you send us your slides, and then we can talk online. Thank you very much. So let's give her a round of applause.
Thank you. I'm going to stop. Oops.
Okay, all the online participants, thank you. I don't know if there's any question, just one question. If there's any question, only one, please.
The very last one.
She has to go, the very, very last one. Okay, there is none. They are clapping for you. Thank you.
Okay, thank you very much. Thank you. Bye-bye.
Have a nice day.
Bye.